Topic 13, 30 and 39, and then a little bit of sound. Should go. I'll try to. I got to go a little bit faster, guys. I got to kind of wrap this thing up. Christian is going to be kind enough to get this thing set up for me so I can get this onto D2L for you guys, not D2L, Canvas. Freudian slip there. I missed D2L, right? I mean, so, but I like them both. They're good. They both have their strong point. Canvas is nice because you can always right when you get to it, you're right on the page. You don't have to go. You don't really have to go hunting for it. So that's kind of good too. All right, let's talk about 13 problems 30 and 39. So let's go. All right, for 13, you guys, let's see what we can say here. Let me get this out of the way real quick. Again, the notes are all there, guys. You've been put between a rock and a hard place. I know that. It's a hard situation for you, but I think this is okay. I think we can do it. I know we can do it. Okay. Forgive that interruption, guys. Let me let's go to 30 and 39 from topic 13. They talk about, again, the equations that are in there, guys, are a real good way. It's not the only way to do this, and it's not necessarily, first of all, it's not the only way to do this, and it shouldn't be the only thing that we're doing. But given our circumstances, if you look at the summary, for example, for topic 13, if you look at the summary on pages 449 to 450, they really give some just decent stuff you can look at as to how to do something like this. They talk about what the period is of oscillation, what omega is, how omega and the period and all these other things relate to one another. And I think it's not a bad way to go. I mean, given the circumstances we're in. I'm not asking you questions that are really as difficult as they could be. And now we lucked out that it's let that way because I don't think we're not in the circumstances to actually look at the stuff the way I think we need to look at the stuff, you know? So let's look at this as is and we'll figure out where we are. 30 from 13, you guys. So again, I'm going to have to, on these last two, you're going to have to look a little bit. I do have a lot of stuff online. I do have it online. Please read my notes online. You can see I'm in the middle of about an 8 or 9 hour endeavor right now, and we're just scratching the surface, you know. So that's not, you know, that's just the way, that's anybody if they were trying to do this. So even after many hours, you're only scratching the surface. So read the notes that I got presented to you about oscillations, about the speed of sound, about the Doppler effect. I even derived the Doppler effect for you. Do you have to do that? No, you don't really have to do that. But a lot of that stuff's already out there. It's there for us. We don't have a tremendous amount of time, but we do got a lot of time. We just don't have a lot of time together. That's what's kind of still got a month and a half or whatever it is. I don't even know what the date is anymore. So I think we're going to be okay, you know, but so let's see what we got. All right, let's see what we can say here. For problem number 30, topic 13, an object executes simple harmonic motion with an amplitude A. Part A, at what values of its position does its speed equal half its maximum speed? B, at what values of its position does its potential energy equal half of the total energy? So let's see what we got here. There's two things here. An object executes simple harmonic motion. It oscillates back and forth like a spring. The ideal spring where you pull the spring and it oscillates back and forth, and there's mathematics to describe that. An object executes simple harmonic motion with an amplitude A. Amplitude is the longest displacement from the center. A. Part A, at what values of its position does its speed equal half its maximum speed? At what values of its position does its potential energy equal half the total energy? So if half the total energy is potential energy, the other half of the total energy is kinetic energy. The total energy is always the same. So kind of get a feel for it, I guess you could say. We are, to make a long story short, if something oscillates in simple harmonic motion, you guys, say there's an ideal spring, And it's right here. The spring is relaxed right here. There's a mass M right here, and the spring has a constant K associated with it. If you pull this mass out to here, a distance x, or a distance delta x, then it'll oscillate back and forth. It'll come over to here. It'll also come over to here, x amount. It'll go, it'll go x. It'll go x this way. It'll go x that way. It'll oscillate back and forth in simple harmonic motion. Its maximum speed is right here. Oscillating this way or oscillating that way, right through the equilibrium position is the maximum speed. And there's no acceleration here. Acceleration's at a minimum right here. Here, velocity's at a minimum, but the acceleration's at a maximum. It's getting yanked really hard to go back that way. Same over here. Acceleration is at a maximum. Speed here is at a minimum. It'll come to a dead stop. It's equal to 0 right here. It's equal to 0 right here. V min equals 0. V max is everything here, but no acceleration whatsoever. The acceleration is 0 right here. Here it's a max. It oscillates back and forth in a very predictable manner. If it's a frictionless environment, it stores that energy forever until it hits something. Until somebody hits him or it hits somebody. But it'll oscillate back and forth and not, So what's going on here? Well, how much energy is in there? If this thing oscillates, just because it oscillates back and forth forever doesn't mean it's putting forth energy forever. There's one set energy amount that's there. So what are you talking about? It's going on forever. Yeah, but there's no friction. There's no friction. It might as well be that you climbed the EMS building and held a shot put and you're about to throw it over the edge into the sand below for the experiment. You're holding it, the energy is stored that way. Here the energy is stored through the oscillation that it's doing, but it's not losing or gaining energy. So it doesn't have an infinite amount of energy. It doesn't have that. Very important. Well, how much energy does it have? Well, how much did you pull it by? Didn't we say that a spring it's a maximum, I pulled it that far, that's how much energy I got. Well, if this is a maximum amount that you pulled it, x is equal to a. In this case, that's the amplitude. It'll go back and forth forever like that. That's the energy. So what's E max? E max is 1/2 Ka squared. Or it's 1/2 M V max squared. They're equal. What does that mean? Well, the spring has no spring in it, right in the middle. Right in the middle, the spring has no spring in it. It's this is all potential energy right here. This is nothing but potential energy right here. Nothing but potential energy right there. This is nothing but kinetic energy. If you add them together, you got the whole energy of the system. You basically got, for 38, I already wrote that, I think over there, I didn't write the A, but the entire energy of the system, 1/2 Ka squared, equals 1/2 Kx squared. That's the potential energy at any one location, plus the kinetic energy at that one location. If this is 0, it's all kinetic energy. If this is 0, it's all potential energy. This is all the energy. It's constantly changing. There's a lot of kinetic, there's all potential energy right here. 1/2 Ka squared. Right here, 1/2 Ka squared. Yeah, no kinetic energy because it's not moving. Here, it's all kinetic energy. 1/2 mv squared, which is as big as 1/2 Ka squared. What happens for the other guys that are in the middle? Well, if you're right here, you're moving and you got potential energy, and we got to add them together. And it's doing this. And it's doing that. So, as you look at it, see where we're at. They want to find out where the location is of this thing. And we'll take it from there. I think they're asking for A. They were saying, at what values of its position does its speed equal half its maximum speed? Speed equals half its maximum speed, huh? Well, there's the amplitude, position of it. Let me see. Half its maximum speed, huh? This guy right here is going to be 1/2 half its maximum speed, huh? Here's max, half. Yeah, it's pretty good to me. Let's keep going. We have Ka squared. It's a 4 on the bottom. You can write it any way you want. Half times, 2 times 4 is 8. I got to ask you a question here. That I think is pretty important. Let me not go there. Let me kind of what I just said is true, but let's get around it somehow. Can I ask you a question? That's a 4 on the bottom. Why don't you bring the 1/4 out of there? And why don't you leave 1/2 m v max squared right here? I do have a question for you. These are equal. And that was max. 1/2 Ka squared is the same as 1/2 m v max squared. Oh, good that. Okay. Yeah, that's visible, right? Is that okay? All right. Guys, 1/2 m v max squared is 1/2 Ka squared. What are we talking about? You'll see what I mean in a second. Equals 1/2 Kx squared plus, be careful now, here's a quarter. 1/4 of 1/2 m v max squared. 1/2 m v max squared is 1/2 Ka squared. Why don't you subtract all this on each side? This right here is 1. This is a quarter. Subtract this on each side. You end up getting 3/4 Wow. What do you say we multiply by 2 on each side and get rid of the halves, or divide by half on each side? And then let's divide by K on each side. We divided by a half on each side. We divided by 1/2 K on each side. How's that? Divide by 1/2 K on each side. Square rooted. Plus or minus the square root of 3 over 2 times A. That's what's coming from. B. B, be, when is the potential energy half as much as the kinetic energy? It's kind of the same argument, you guys. It's kind of the same darn argument. Here's the total energy of the system. 1/2 kx squared plus 1/2 mv squared. Wait a minute. If half the potential energy is half the energy of the system, if this guy's half the energy of the system, so is this guy. Look, man, if you got $100, if I have $100 and only 2 people own that $100, and you have half of it, what do I have? I've got the other half. If this is half the potential energy, if 1/2 kx squared is half the potential energy, this guy right here is also, this is half the maximum potential energy. This is also half the maximum potential energy, because the maximum potential energy is all of the energy. If this is half, this is also half. So what does that mean? It means a lot of stuff. It means this and this are equal. So there's 2 of these 1/2 kx squareds at that point. There's a lot of ways to write that, but I mean, there's the easiest way. Okay, 2 times 1/2 is just kx squared. This is 1/2 ka squared. Be my guest. What do you say? Divide by k. Divide by k on each side. Square root each side. Sometimes they don't like the irrational number in the denominator, so they rationalize it and they make square root of 2 times a over 2. Either one's fine. They mean the same thing. Square root of 2 goes into 2 square root of 2 times. Put this down here. This goes into here, square root of 2 times into this. I like this one more, but it's usually not the way they write it. You write it like that. Doesn't matter much. I mean, it should be all right. That is 30, all of it. Let's do 39. Thirty-nine is saying the free fall acceleration on Mars is 3.7 meters per second per second. A. What length of pendulum has a period of 1.0 seconds on Earth? All right, I don't like the way this is asked, but let's kind of look at it a little bit. I'll read it and I'll try to make some sense out of it. 39. The free fall acceleration on Mars is 3.7 meters per second per second. Compare that to Earth, guys, which is 9.8 meters per second per second. A. What length of pendulum has a period of 1 second on Earth? What length of pendulum would have a 1 second period on Mars? An object is suspended from a spring. An object is suspended from a spring with force constant 10 newtons per meter. Find the mass suspended from the spring that would result in a period of 1 second. C, on Earth, and D, on Mars. Okay, they ask a whole bunch of stuff. Let's talk. I do give relatively comprehensive coverage in my notes on oscillations. Just look up oscillations on Canvas, read that. You got it? That's part of what this stuff is. I'm going to try to keep it reasonable, guys. I'm going to see what everybody around me is doing and what my bosses are doing and the whole thing. Especially what suggestions I get from people above me, obviously from administration and people who and people who know a lot, who are very, very, very good at what they do. Got to find out what they're doing as well on this stuff, guys. But I'm going to make it reasonable. I think the way we've been told to do this is going to be reasonable for you guys. So what are we talking about? What do you want to talk about regarding this? I can look at it and try to answer the question to the best of my ability. The way they ask it's a little bit more. Every one of these questions is a little complex. That's just how physics questions get asked. You got to read them 2 or 3 times before they make any sense. You got the notes. You can look at it while I'm doing it, guys. Let me run through it so at least I can get you guys through where you need to go, and we can figure it out. All right, guys, you're talking about the pendulum. There are, like I said, in my notes, I give a pretty decent derivation of what's going on and how the period of a pendulum depends on numerous factors. And so I gave some derivations related to it. I think you'll like it. Should be pretty decent. The book does a pretty good job too. Obviously the book does a good job. The book does a great job. Different books do different things. This book does a lot of great work and a lot of things, so I'm sure it's going to be fine. I also do have things derived that I can't derive again. I don't have the time. I do have them derived. They are in front of you in Canvas. Okay? So that's not going to be an issue. If you look them up, you're going to be fine. Look at them. Those of you with a calculus background, you might like some of the calculus treatment that I do in some of the stuff. At this point, we're not going to worry too much about things like that. So I'm breaking every single piece of chalk here, man. I feel like Bruce Lee or something, you know. All right, so here we go. Again, they ask a whole bunch of stuff, guys. What's going on here? The way out of this thing, though, there's a bunch of stuff they say here. If you're talking about pendulums in general, guys, it depends on the G field you're in. Remember, G, that small g depends where you are. On the moon, small g is 1/6 what it is on Earth. On Mars, it's about 40% or something of what it is on Earth. So there's a lot that goes on here, guys. Let's take a look. So for 39, T equals the period of a pendulum, the length of the pendulum divided by the G field that you're in. That G is a different thing if you're on Mars or on Jupiter or on Earth, right? Potentially it's very different everywhere you are. So this is what we know regarding this stuff. We also know that omega is 2 pi f. We know that f is 1 over the period. We know the period is 1 over f. So omega is also 2 pi over t, which means t is equal to 2 pi over omega, which means f is omega omega over 2 pi. So there's a lot going on here. Anyway, in some way or another, we've seen this stuff. We haven't seen it like I want us to see it, but we've not seen each other that much. So it's a rough one for us to get through on this whole process. But this is something they talk about. All right, what is the length of the pendulum given all of this mathematical reality? Especially given this mathematical reality. Solve for capital L in plain English. That's fine by me. Square both sides, and then multiply by g over 4 pi squared on each side, you'll be fine. If you if you do the mathematics, guys, play the game here. Try to cut down. Okay, so this is nuts, man. All right, let's figure this out. Let me square both sides, and then let me multiply by g and divide by 4 pi squared on each side. I'll have L all by itself. So let's see here. I got L right here. I'm going to square both sides, so it's going to, and multiply by g. So g t squared square both sides. Square both sides, square both sides, multiply by g, then divide by 4 pi squared. This is basically the ticket getting you the L. So let's see what we got here. You're gonna plug in all the appropriate values and see what's gonna be said here. So for this one, I mean, this is really the key. I'm not going to be able to emphasize this enough, I think, but it's the key to a lot of what we're doing. Very important. So here it is. Let's talk. I mean, the way they said it, these problems, they just cannot be read one time. I mean, A, what length of pendulum has a period of this much on Earth? I'll tell you how much a period of this much on Earth. If it's a period of 1 second, we're talking about Earth now, right? A period of 1 second, put 1 second right here. 1 second right here, squared, is still 1. So put 1 right here, square it, multiply it by 9.8, and divide by the product, 4 pi squared. When you do that, just plug all that stuff in there, guys. Is that clearly written? Is that written okay? Visible? Okay. All right, guys. It's this thing right here. I don't want to bleed on their board either. It's okay. All right, so we got this. So, L is the 0.25 meters, which is L is equal to 25 centimeters. They usually make it clear what they're asking you. They're asking you something. That's A. B. What length of pendulum would have a 1 second period on Mars? Okay. Go right here. Put 1 right here. Square it. 1 second period on Mars, huh? 1 second period on Mars. 1 second squared is 1. G on Mars is not 9.8. It's 3.7. 4 is 4. Pi squared is pi squared. It doesn't have to be as long to do it. I have about 40% of the length, thereabouts. So what do we got on this one? We got 9.4 centimeters on this one. This one's going to be on Mars. Is going to be 0.094 0.094 meters. We said it was somewhere in the ballpark of 40%. The G, it don't need to be as long. It doesn't need to be as long, it ain't getting pulled as hard either. You throw that, you put that on Earth, it's a different dynamic. Different dynamic. I mean, it ain't gonna work. That kind of period ain't gonna work there. You throw something that short, the period's gonna be a lot shorter. On Earth, a short thing like that, it's not gonna be 1 second. It's gonna be less. It's gonna go faster. It's gonna oscillate faster. To do a whole cycle is gonna take less time. So on and so forth. They're asking here, guys. I mean, they're asking a whole bunch of stuff here. An object suspended from a spring. If you're going to do it with a spring, you guys, it's kind of the same dynamic. It's just a little different look to it. For a spring, you're remembering that you got omega equals 2 pi f, and there's that whole song and dance, that we did over there. It's got all that. Omega is 2 pi f is equal to 2 pi over t. And by the way, I mean, this is something given to you. They can derive it, unfortunately, and I do have it derived. I do have this derived in the notes. The book should have it derived. I haven't looked too closely. I do have it derived for sure, and I'm sure the book does at some point as well. But I have it derived for you in the oscillation section and some other stuff you can look at. So it's all there. Omega is this for a spring. This is for a spring. Omega is this. And you know what else omega is. It's all this stuff too. But omega is this, the square root of the ratio. The square root of the ratio, K over M. Well, let's do the song and dance, I guess you could say. Let's try to get a period here. Let's work with this. Let's flip both upside down and then multiply by 2 pi. For this right here, for all this right here, you guys. If they're equal, the reciprocals are equal. If these two things are equal, get the reciprocals and multiply by 2 pi. You're solving for t then. It's not k over m, it's m over k now for that. What mass object would do that for you? Now they want you to solve for the mass. Okay. Wow, it's kind of weird. It's kind of like the L over there and the G. The G is a lot like the K, and the L is a lot like the M. The mathematics is pretty striking. Look, let's make a long story short. Let's solve for M, right? I think they want you to solve for M. Square both sides, multiply by K on each side after you do it, then divide by the square of the quantity 2 pi. The square of the quantity 2 pi. Make a long story short. You solve this. Do the mathematics, you guys. When you do it, square both sides, multiply by K. Wow, I mean, the similarities in the mathematics are, for lack of a better way to put it, it's pretty striking. So you got that. M equals KT squared over 4 pi squared. What does it say? This is independent of G Mars, G Earth, so M is same for C and D. This is crazy. Look what just happened. You had a spring hanging there. Notice the strange thing about this thing hanging with the spring. There was no G to begin with. In this case, it didn't matter. What are you talking about? I'm not saying there's not going to be other peculiarities that are going to happen mathematically. There are going to be other peculiarities that happen mathematically. They're going to be very interesting. In this particular process, it doesn't matter what gravitational field you find yourself in. You could be on Jupiter, you could be on Mars, or you could be on Earth, or you could be anywhere else. K and the M are what run the show here. The spring constant and the mass. So this is independent of G Mars, G Earth, or whatever, honestly. So M is same for C and D. The mass is the same for both of those. By the way, what is that mass? Well, I mean, here's C. Here's D. We just said it's going to be the same. Plug in, I think they were saying for 1 second, right? Put 1 second here, put the spring constant that they gave you, divide by this product. And the mass that does that, no matter where you are, they're the same, guys. So let me try to forgive me here. I probably wrote it good enough, but Is that okay? That's okay, thank you. 0.2533 kilograms for C and D. What are they saying? I mean, they're saying, they're saying here, okay, an object is suspended from a spring with force constant. The force constant is 10 newtons per meter. Find the mass suspended from the spring that would result in a period of 1 second. C on Earth, D on Mars. It don't matter. So they said this was, I think, 10 newtons per meter, 1 second right here. 4 is 4, pi squared is pi squared. Do what you got to do. It's not going to matter. This is independent of G Mars, G Earth. And that is it for that one. That's it. We just got 14 to do and be done with this thing.